Hello Bobcats. In today's video we're going to discuss transferring energy. Now remember, thermochemistry is the study of the transfer of energy during physical and chemical processes. So we are going to now discuss transferring energy as part of thermochemistry. What's involved in transferring energy? Okay, so there are two ways that energy can be transferred. Into or out of a system. Okay. The first way is work. So let's talk about work. There's two definitions of work I'm going to use. Well, one definition, but two equations. So first, let's talk about work. We said that work is one way that energy can be transferred. So work is with a W and is defined as energy transferred when a force moves an object a certain distance. Okay, now work is very much related to energy, and let me explain this. Hopefully I can do this on this video real quick. So let's use this pen, and let's say the pen is has no energy relative to it sitting on the desk. If I apply a force and move it, now I have moved it a certain distance above the table. That's the amount of work that I've done. Well, that amount of work is also equal to the amount of potential energy that this pen has at this distance above the desk. When I let it go, it drops and it moves, it changes to kinetic energy. So the amount of work that I do is the amount of potential energy that I'll have, which then is converted to kinetic energy as it falls. And they are all interchangeable and equal to each other. Now, the equation for work, so work is equal to force times distance. That's the equation we use in physics. Now let's look at the units for this, okay? Now remember, the unit for work, we said, is going to be a joule, and force is a Newton times distance, which is a meter. Okay, so this is the unit of a joule is equal to a Newton times a meter, but the Newton is also a derived unit, so we kind of have to break that down. So if I look at it, a joule is equal to now Newton. Force is mass times acceleration. So mass is that, acceleration is meters per second squared, and then times a meter. So this is also meter times meter. This is also a kilogram meter squared per second squared, which is the same unit that we saw when we did potential and kinetic energy. Now, in chemistry, the work equation that we use in chemistry is what's known as a pressure-volume work equation. So in chemistry, we look at work is equal to negative pressure times a change in volume. Okay? Now, this equation also will have units that work out. Let me get a different pen. That one was running out. And I apologize, I've got really bad allergies today, so I keep sniffling. But pressure, if we look at the units for this one, let's make sure the units work out. So pressure, okay, remember we're looking at work is a joule. Pressure is really a Newton per area, force per area, or Newton over meter squared. And volume, remember, any volume would be like meters cubed. Okay? So when we do this, remember that will cancel that, and so it's a Newton times a meter. Remember Newton meter, so that all comes out to be a kilogram meter squared over second squared. So it comes out with the same units. It's just that we use pressure and change in volume for work when we're talking about chemistry. Now there is an important thing here. There's a unit conversion for this. Let me put it in red so you'll see that. The unit conversion for work pressure, let's write it here as a pressure volume unit conversion okay, so 1 liter times 1 liter atmosphere is equal to 101.325 joules. So we have a unit conversion. I know you're saying, wait a minute, did I just show you that these units work out the same way? And yes, it does, because pressure is force over area, and volume is distance cubed. But remember, most of the time we use liters and atmospheres. Liters for volume and atmospheres for pressure. So an easy conversion would be 1 liter atmosphere is 101.325 joules. Again, excuse me for sniffling. My allergies are really bad today. Now, so we can transfer energy through work, and we can transfer energy through what we call heat. So the other way to transfer energy is heat. And heat is represented with a Q, and is the energy transferred from a hotter object to a colder one. From an object of higher temperature, which is hotter, to an object or substance of lower temperature. It's always from high to low. You don't ever go backwards. You don't go from low to high. You always go high to low. And what's important is to be able to discuss this in molecular terms. So let's see what that means. So you need to be able to discuss in terms of faster moving molecules. Okay, remember, the faster the molecule that's moving, the higher the temperature that's recorded. So faster moving molecules colliding with slower moving molecules or lower temperature. Moving molecules and transferring energy until a thermal equilibrium is met. Okay, and what I mean by this is to be able to think of this. So if I have a really fast moving molecule and it collides with so we got a fast moving molecule here and a slow one here, and the fast one collides with the slow one, it transfers some of its energy, and you wouldn't understand that when it hits, the slow one moves faster and the fast one moves slower. So because it transferred energy. But the energy before and after is always the same. And eventually, after they hit each other enough, they end up with the same amount of kinetic energy or velocity, and we call that thermal equilibrium, or the same temperature. Again, remember, it's always high to low. Always high to low. Now, we need to talk about internal energy and energy leaving and entering a system. So, here's the two ways we can transfer energy. Now let's talk about internal energy and how we use that to determine if something's transferred into energy is transferred into or away from a system. So, let's do internal energy. Represented with a capital E, and I'm going to go ahead and show you, or it could also be represented with a capital U, and I think in engineering they use a U. In chemistry you use an E, but your book uses U. Almost every other book I know uses E, but I'll put them both up here so if you see them you'll know that they're both interchangeable for internal energy. And internal energy is the sum of all of the kinetic and potential energies in a system. Okay. Now, usually we do not discuss internal energy itself. It's very, very difficult to come up with a value for. If I were looking at my desk right here, all these molecules in this desk are moving. They have some kinetic energy because they are under vibration, but they also have a lot of potential energy because they're bonded to each other, and there's a lot of attraction. And we know that because if I take the desk and I start it on fire, it's going to continue to burn or release energy. So there's a lot of potential energy here, but there's also kinetic, but it's hard to know or calculate or put a numerical value to a system's internal energy. So what we really look at is the change in energy of a system. So I'm going to write this. So really we want to look at delta E is equal to energy final minus energy initial. And we're really wanting to deal with this. And you can think of this also as, since this is the final energy, that would be the energy of the products minus the energy of the reactants. Okay. Now, this is the first law of thermodynamics. So I'm going to write that out. Now, we said that the first law really is stated as energy cannot be destroyed, created or destroyed, only transformed from one form to another. So, but I'm going to state it in a different format here, but it's the same thing. So the first law of thermodynamics is a change in energy of a system must be accompanied by an equal and opposite change it's an I, sorry, opposite, couldn't spell very well there, opposite change of energy in the surroundings. Because energy cannot be created or destroyed, it just goes from one form to another. So there's got to be an equal and opposite energy of the surroundings as there was lost in the system. Now, in equation-wise, what that looks like is this. It would look like, we would say, the change, trying to get different color, the change of internal energy of the system is equal to a negative change in the energy of the surroundings. Okay. And that's really the first law of thermodynamics. Now, so how does that look? Let's go through this and look at a system and how does that work. So, if I have, let's put a square and make the square the system, and then everything outside that square is the surroundings. And we have energy leaving the system and going to the surroundings. Leaving the system and going to the surroundings. You might think of it as this. Let's look at it in this format. Let's say I have, this is energy increasing going up, okay? And let's say I start out with my initial energy, and then I have my final. Okay, and so as I lose energy this direction, I have to release that energy. So as I go down in energy, that from a high to a low, energy's got to go somewhere. And so we have to release that energy from the system. Okay. So in this case, we are looking at energy of the system is going to the surroundings. Equal and opposite, okay? And in this case, the energy, the final energy is going to be less than the initial energy, okay? And so if I take final minus initial, remember this up here is final minus initial, then my delta E is going to be less than 0, which means it's negative in value, and we call that exergonic. If we're just talking about energy, it's exergonic. If we're talking about heat energy, it's going to be exothermic. And we'll get back to that in a minute. So, as energy leaves, the surrounding is going down in energy, and because the surrounding is going down in energy, it's going to be less than 0 or negative. It's going to be negative. It's going down. It's losing energy. So it's negative, exergonic. Then the other one is, let's look at the surroundings. So here's my system. The outside of the system is the surroundings. And here we have energy entering the system. So energy is going into the system. Okay, and so again, another analogy, if we look at this, with energy increasing as you go up, let's say our initial energy now is low, so the initial energy of the system and remember, is low, and we add energy to it, so the final energy is higher than the initial, so we have to go up in energy, and that means you have to absorb energy to go up, so energy is absorbed. And in this case, the energy is going from the surroundings into the system. Okay, and so now the system is increasing in energy. And now my final energy is greater than the initial energy of the system. And so the change in energy is greater than 0, or positive, so it's a positive value, and we call it exergonic, or endergonic, sorry, endergonic. And the way I remember it is that energy is entering, or going into, and so endo sounds like it's going in. Okay, so that's the first law of thermodynamics, in that we have energy going into the system or out of the system, but whatever change in energy of the system has to be equal and opposite to the change of energy of the surroundings. And then there's values over here that we can see, positive and negative values. So let's go back to this idea of transfer of energy. So let me make this statement here. I should put it on here real quick. One last thing to say. So the internal energy of a system remember, we want to look at the systems. I think, though, in engineering you look at the surroundings, but in chemistry we look at it through the system. Can be changed. Okay, so remember, we can do that by, we can change the amount of energy in a system by a flow of work, heat, or both. Okay, and so there's an equation that's really important to go with this one. And this is the equation you really need to know, is that the change in energy in a system is equal to the heat plus the work done on the system. Okay, so you need to know this. I'm going to put a star right next to it, okay? Even though it's the last one on this page, it's still very important. Okay, now, so let's talk about how that work and heat flow affects our system. Now, just a reminder, this is really important, thermodynamic or thermochemistry, dynamic quantities always consists of two parts. And you make sure if you miss a part, you get it wrong. You have to have both parts. So two parts. First is a number or value giving the magnitude of change. And then the second part is a sign, positive or negative, indicating direction of flow. in or out of the system, okay? Now, also you need to use your units, joules, but we want to make sure you know that there's got to be a sign with it. I had a lot of trouble in thermodynamics when I was in college because I kept forgetting to put the correct sign. And by the way, the sign reflects the system, the system's point of view. Okay. Now, so energy into the system. Repeat this again. It's so important to understand this kind of stuff. Energy into the system is positive sign. Remember, you're increasing the amount of energy, so you're going up in energy, it's a positive sign. Energy out of the system is negative because it's going down in energy. You're losing energy, so it's negative. Okay, very important for you to understand. And just as we had the first law of thermodynamics saying that the energy, the internal energy of a system is equal to the negative internal energy of the surroundings, we do the same thing. So the heat of the system is always equal to a negative heat of the surroundings, or we can say the work of the system is equal to a negative work on the surroundings. Okay, it's obeying the first law of thermodynamics. So let's go through this. Heat flows, let's look at heat and then work. So 1, if heat flows out of the system, so let's look at it as heat flows out of system, flows out of system. So we have a negative Q, and it means system loses energy. And we would say that this is exothermic. Because it's heat, right? Not exogonic, but exothermic. Now, one important thing to think of is that the surrounding gains energy, and therefore the surroundings are warmer. That's why exothermic reactions give off heat, because they're actually the reaction itself is losing the energy, and the surroundings, which is everything else, including you and me, is getting warmer because the surroundings is gaining the energy that was lost by the system. Okay, number 2, heat flows into system. Okay, so in this case, we have a positive Q, and it means system gains energy. And so if it's gaining energy, it's absorbing, or endothermic. The system is absorbing the energy, it's becoming endothermic. And in this case, the surroundings loses energy and therefore is cooler. Remember, these three dots like this is therefore, shorthand for therefore. Okay, now we need to look at work. So number 3, work done by system on surroundings. Work done by system. And then just on surroundings. Now again, I'm going to use a piston idea because that's where the pressure volume work comes from in chemistry. So if I have a piston like this, and then in that piston, okay, there's solid form. Now, if we have a negative work means energy is transferred to surroundings. By doing work. Okay? And think about it, if we have a system, and in the system, if you do work, in other words, if the piston moves up, the system is doing the work, and it's losing energy to the surroundings by doing work. And usually, we can think of this as expansion. Okay, so I have a reaction that goes on that creates a pressure, but we have to keep the pressure constant, so the volume changes and increases, and as it increases, work is being done by the system, and therefore it's a negative W because it's losing energy to the surroundings. Okay. And then I don't have room on this page, so I'll go to another page to talk about work done on system. And then we're going to do a quick a table and a practice problem. So 4, work done on system. By the surroundings. Okay, now let's do the piston again. Here's my system. And in this case, work is being done by the surroundings on the system, so the piston goes down, but it's the surroundings that are doing the work on the system, and so we get a positive W, meaning energy is transferred to the system, by work being done on system. By work being done by surroundings. Now think about it. Remember, if I push this in, we're going to add energy into this system. Just like when I pick this pin up, I'm adding energy, potential energy, into my system, which is the pin now, which is above. So I've done work on the pin, and now it has gained energy, potential energy. Just like this, work has been done on the system, so the system gains energy. You can think of this as compression, and compression is a result of work done on system. Okay, and that's how our combustion engines work. That's how we get our cars to do what they need to do, because we're either doing work by the system or on the system, and our system would be a piston. So let's look at a table real quick of what these would look like. So remember, if we have Q plus W equals delta E, or the change in energy, and let's say we have positive Q. What's positive Q? Positive is work done, or heat flowing out into the system. So if we have heat flowing into the system and work done on the system, then we're going to have a positive delta E. If we have heat flowing into the system and work done by the system, it all depends on your values. And then if we have heat flowing out of the system and work done on the system, then this also depends on Q and W values. Meaning that if this is a higher value than this, then it's going to be a positive delta E, or if the heat lost by the system is higher than the work done on the system, then it's a negative delta E. And then if you have negative for each of these, then you know that delta E is negative. And so this would be exothermic, and this would be endothermic. Okay. Now let's do a practice problem. Make sure everybody has that down. Okay. A reaction occurring in a flask releases 890 joules of heat to surroundings, and the gas that is produced performs 450 joules of work on the surroundings. Okay. By pushing the piston upwards. Okay, I'll try to do the best I can to draw this. So it's kind of like if I have my piston here, and it's connected to a flask here, and then I'm going to just draw a line. So this is the flask down here. But we have the piston, and you have an initial volume here. So my initial volume, and then we have a piston, the same piston. Again, this is the flask here that I'm trying to show you. I'm not going to draw a flask because I'm not too good at it, but it's connected to a flask. And then this is where the piston ends up, so that's a final volume. Okay. So first we need to, A, is this a closed, open, or isolated system? And why? Explain. B, determine the signs of Q and W in this reaction. Of heat and work in reaction. And C, determine the change in energy. Determine change in energy, or the delta E for reaction. Okay, so first thing is it an open or closed system? So when I look at this, it's not open, it's closed, because the flask that I'm not showing is a closed flask, and this is just a tube that takes it to the piston. If you want to look at it, I've got it drawn right here. So it looks like this, so we know it's closed. So we say that this is a closed system, and explaining that, so this is a closed system because energy but not matter can flow between system and surrounding. Kelly, can I call back? I'm making a video real quick.
Oh, I'm so sorry.
That's okay. Love you.
Bye.
Bye. Sorry about that. My wife just called. I should have had the phone turned off, and I forgot to turn it off. So I apologize for that interruption, but we're almost done. B. So for B, we need to find out if Q is a positive or negative. So let's say energy is released from system. Therefore, it's a positive. No, it's negative Q. Negative Q. Energy is released from system to surrounding, so it's negative Q. And then in this case, work is done by system. And so also energy is going from the system to the surroundings because work is done by the system. So this is a negative W. And then the last is C, where delta E is equal to Q plus W. So delta E is equal to, and in this case, remember, energy was, the heat was 890 joules and the work was 450. So that's a negative 890 joules plus a negative 450 joules. So the delta E is a negative 1340 joules of energy. And we really like to say that the delta E is a negative 1.34 kilojoules of energy. Okay, so that's how we look at what's going on with energy. We can either transfer energy through work here, W, or heat. And our next video is all about just the heat. We're going to forget about the work. And I'll see you in the next video. Thank you.